So today we're going to see how we can solve the overfitting problem in classification. Last week we saw this for regression. Now we're going to apply the same thing for classification, and we're going to look at a better method for doing things like selecting models or adjusting regression parameters, which is an extension of that validation method we saw last week. So this is cross-validation. But first we're going to see how we can score classifiers. We're going to look at cross-validation, and then we're going to see some examples using logistic regression, which was the classifier we looked at last week. And we're going to do model selection and regularization with logistic regression. So these are two different methods to try to solve the overfitting problem, trying to prevent fitting too much to the noise of the data that we have, and then lose the ability to predict correctly outside the training data. So first, let's see how we can score classifiers. We saw in regression that we wanted to fit the line by minimizing the quadratic error. So this quadratic error would be a natural way of scoring how well our regression was made, how close to the point our line was. So this was basically the function, the error function we were trying to minimize, and the same function we could use to evaluate the regression curve. With logistic regression, we are also doing a regression. So we can use the actual function that we are minimizing. Remember that with logistic regression, we are trying to adjust our parameters so that we fit an hypothetical function that gives us the probability of each point belonging to each class. Then we use that to draw a line on the region where the probability is 50%, and that is our discriminant. But we are using that discriminant to classify, but we are actually computing a regression trying to find the best way to predict those probabilities. And since we are minimizing this cost function here, we can use this score to evaluate logistic regression too. But there are other ways of classifying in general, of scoring classifiers in general. So this, in the case of logistic regression, this formula actually is the equivalent of the cross-entropy function. So it's one way, we're using the same score, and it's one way of evaluating logistic regression classifiers. But more generally, we can, if we have a classifier that predicts the probability of each point belonging to one class, so say class 1, for example, we can use this prior score. This is also a quadratic error, but note that this is not a quadratic error measured as the distance to the discriminant. This is different. We are measuring the quadratic error of the probability predicted by our function and the actual class the point belongs to. So for each point in our data set, we know that if the point belongs to class 1, the probability of belonging to class 1 is 1, because we already know it belongs there. If it does not belong to that class, the probability of belonging to that class is 0. So these, for each of our data points, we have either a probability of 1 of belonging to that class or 0. And then, after we train our classifier, as long as our classifier can give us an estimate of the probability of the point belonging to that class, as happens in logistic regression, we have this value predicted for each point. So if our classifier predicts a 90% probability of the point belonging to class 1 and the point belongs to class 1, the error is only 1/10. So we can do that for all the points, and this is the Breyer score. So basically it's the quadratic error on the predicted probability of a point belonging to a class, and we can use this for any classifier that can predict that probability. So this is more general than just for logistic regression. We can illustrate this with a logistic regression. If we plot, we have a two-dimensional data set, but we can use the third dimension to separate the two classes. This 0 here is class 0, this 1 here is class 1. And we train our logistic regression to predict the probability of a point in anywhere in this combination of two features, the probability of belonging to class 1. So this is the curve that we get from our classifier. And now we can measure the Breyer score by measuring the error between the predicted probability and the actual class each point belongs to. As long as your classifier can predict this probability, you can use the Breyer score to evaluate the classifier. Another way of doing this is creating a confusion matrix. We are seeing this in 2 dimensions. This can be generalized for more than 2 classes. However, we're going to, for most of the semester, look only at binary classification. Then we'll extend this for more than 2 classes. But the idea is that each example can belong to class 1 or class 0 or class A or class B or red and blue, whatever we can call it, and we predict which class the example belongs to. So if it belongs to class 1, if it belongs to class 1 and we predict it to belong to class 1, this is called a true positive. It belongs in positive class and we predict it to be that. If it belongs on the negative class or class 0 and we predicted it to belong to class 1, this is a false positive. We think it's positive, or our classifier thinks that point is on the positive class, but it's false. It does not belong there. Then we have the same thing here. If it belongs in class 0 and we predict that it belongs in class 0, it's a true negative. It's a negative point that was correctly predicted. But if it belongs in class 1 when we predict it belongs in class 0, it's a false negative. We are saying it's negative, but that's false because it's actually on the positive class. So if we count how many times each of these occur, we have a matrix that can tell us not only when our classifier gives us the right prediction, which would be in this diagonal here, but also how many times it makes and which kind of mistakes. Note that in general we are not going to worry about the different kinds of mistakes, but for practical applications some types of errors may be worse than others. For instance, if you're diagnosing cancer, it may be better to have some false positives and then repeat the analysis, rather than having false negatives and you let people go who actually are sick and should be treated. So we may have to weight the different errors, and with a confusion matrix we can actually see what kind of errors our classifier is making. Then we can use those counts, the true positives, true negatives, false positives, false negatives, to get some scores to quantify some aspects of our classifier. These are 3 most used. So one, accuracy is the number of correct predictions, so true positives and true negatives. These are the points that are predicted to be in the class where they actually are, divided by the total number of points. So this basically tells us the fraction of points in our data set, for instance in the test set, that our classifier can correctly classify. Precision tells us when our classifier is telling us these points belong to the positive class. Precision is a measure of how many points are actually correctly placed in that class. So this is the true positive divided by the total number of points our classifier thinks are positive. And recall is the number, is the fraction of elements of examples in the positive class that our classifier can get in its prediction for the positive class. So it's those that are correctly classified as in the positive class divided by the total number of points that should have been classified in the positive class. And the difference between precision and recall basically is, in precision, this is the fraction of good results you get in the results that are given to you by the classifier. If you imagine this as search results, for example. So you get a page of results, and they are, if the precision is high, most of them are good results for you. Recall gives you a measure of how many of the results you wanted to appear on your results page are actually there. So if you get all the good pages that you are looking for in the results page, then there is a high recall. Of course, if it's mixed with a lot of garbage, then you can have high recall and low precision, because you have all the good results, but they are mixed with a lot of things that should not be there. Then you have derivative scores from this. For example, the F1 score is the harmonic mean of precision and recall, and you can weight the two and give an overall estimate and so forth. So there are, this is to give you an idea that there are many different ways of scoring the performance of the classifier, and they depend a lot of what you want to do with the classifier. So, for example, if you are optimizing search pages for Google, then probably you want that in the first page there is at least one or two very good results, because the person looks at those, clicks, and it doesn't matter if there are other results that are wrong. But if there are no good results on the first 3 or 4 pages, then people will not use your search engine. So you may want to optimize some things depending on the application. Another way of scoring binary classifiers is to look at what happens when we change the cutoff points to decide where we put one class or another. Remember that in logistic regression we decided to put the discriminant hyperplane or discriminant line in 2 dimensions, but a hyperplane in n dimensions. We decided to put it in the region where the estimated probability of belonging to one class is 0.5 and 0.5 for the other class. But this is an arbitrary choice. We could have decided to put the discriminant in the region where the estimated probability was 90% one class, 10% the other, or vice versa. So we could change this place where the discriminant is placed, and basically what we are doing is moving up or down this slope here and deciding to cut the 2 steps in different points. So what we can see what happens as we change that position. So suppose that we put our threshold at 0. If we put our threshold at 0, we're actually saying that everything belongs to the positive class, because there is no estimated probability below 0. So if everything belongs to the positive class, this is an example with 90 points, 45 on each class. If we assume that they are all in the positive class, we get all the positive class points correctly. So our true positives are there at the top. However, we also say that all the negative points are positive. So these are the false positives that we have, and they are all way up there too. So this is not very good, because basically we're saying everything is red, even though half of the points are blue. As we increase the threshold, we start making less mistakes on the blue side, on the negative class, because we start moving over here and we start discarding these points from our predicted positive class. So the false positives start decreasing, but at some point we reach here and we start also losing true positives, because now we start classifying some of the positive points as negative as we increase the threshold. And it's intuitive to see that the larger the distance between these 2 lines, the better our classifier will be, because we can find the best spot there where we separate the 2 as wide as possible. So we can do this. We can plot this in another way, which is for each value of this threshold, we count how many false positives and how many true positives, and we plot the line of true positives versus false positives. And this is the receiver operating characteristic curve. This is a strange name, because this curve was initially used during the Second World War to evaluate the performance of radar operators and their ability to distinguish between enemy airplanes and rain or flocks of birds and things like that. So they had true positives and false positives, and they had to weigh the 2 to try to evaluate the performance of the operator. And what we're seeing here is that if we have a 0 false positive rate, we have this true positive rate. So basically we are looking at this edge here when we don't have false positives. As we increase the false positive rate, that is, we decrease our threshold and allow more things to be classified as the positive category, we also increase the true positive rate, because now we are not losing those examples, but we are increasing the false positive rate too. So if we have a classifier that has absolutely garbage performance and works at random, basically, we should have something like this on this line. As we increase the false positive rate, the true positive rate would increase too, but they would just accompany each other. The further away the line gets from the diagonal, the better our classifier is at distinguishing the 2 categories. So one one measure we can use to score a classifier, to evaluate a classifier, is the area beneath the ROC curve. The higher this area, remember this is normalized to between 0 and 1, these are fractions, so the larger this area, the better our classifier would be. A perfect classifier would be one that for 0 false positive rate had a 1 true positive rate, so it could distinguish everything without making any mistake. So basically, to score binary classifiers, we can use the actual target function depending on the classifier. So for logistic regression, one thing we can use is that loss function, which corresponds to cross entropy. If a classifier gives us an estimated probability of each point belonging to one of the class, we can use the Breyer score, which is simply the quadratic error between the predicted probability and the class the point belongs to. We have also these measures when we look at which points were correctly classified or incorrectly classified in each of the categories. We can measure precision, accuracy, recall, and then all the derived measures from there. We can build a confusion matrix to have an idea of the different types of errors, and we can also use this receiving operator characteristic curve to evaluate the classifier by measuring the area below the curve. Classifiers in scikit-learn include, so the classifier objects in scikit-learn include a score method that returns accuracy. So it returns the fraction of examples that were correctly classified. For instance, if we use the logistic regression object, we can use the fit method to adjust the model, and then it computes the parameters, and then we can measure the error from the accuracy. So we use score, we give our data and the class, so the features and the correct classification. This method will use the hypothesis that we fit before to do the predictions, and then compare with the labels for the class, and give us the percentage or the fraction of examples that were correctly classified. So if we want the accuracy, we use the score. If we want the error, we use 1 minus the score, because those that is the fraction that was incorrectly classified. So now let's see how we can, using some methods to evaluate our classifiers, how we can select either the best model or adjust the parameters for regularization. So previously what we saw is that we needed to split our data into 3 sets. We use one set, the training set, to adjust the parameters of the model. Then we use the validation set to measure the error on that hypothesis, so to have an estimate of the true error for that hypothesis, because if we measure the error on the same points that we use to fit the parameters, it will not give us a good estimate of the true error. And then we can do that for different models, and based on the estimated true error for each hypothesis, we can select what appears to be the best model. Since we are selecting in order to minimize the validation error, now this estimate will no longer be an unbiased estimate of the true error, because we are deliberately choosing the smallest one. So we keep another set outside, the test set, so that at the end, after we choose everything, we can get an unbiased estimate of the true error of the final hypothesis. Now, one problem here that we saw is that we are training the model with one set of points, and then measuring the error on the validation set, but if the points were shuffled differently, the measured error would be different. So we saw this example. For the same model, we get different curves depending on where we put our points in the training or validation set, and different estimates of the error, because we are using a random sample of points. So one better way of doing this would be if we could do this several times and then average the results. So we would have a better estimate of the true error of that model when, in general, it is trained on this kind of data. So this is the basic difference here. Instead of evaluating the model by looking only at one hypothesis and measuring the error on the validation set, we are going to try to evaluate the model by estimating its true error over several different hypotheses. And this we can do with cross-validation. So we're going to, this is typically, we're going to leave a set of points outside the test set so that at the end we can get an estimate of the true error of the hypothesis. And now the training set, we are not going to separate it into training and validation once. We are going to split this training set into n folds, more or less of the same size. So an n-ary partition of the training set. Now what we're going to do is to train an hypothesis with n minus 1 of those folds, leaving one of the folds out. And that one that is left out is used to compute the validation error. But now we're going to do that for each of the folds. One time for each fold, we're going to leave that one out and train with everything else. And then we're going to average all the validation errors. So to illustrate that, this is our data set here. I'm representing the data points all in an array there, so they are shuffled, they are blue and red, they are mixed together. And we can imagine that we're going to split this set into 5 almost equal parts. Sometimes you don't have a multiple of n, so some groups may be a bit smaller, but the idea is to split it as evenly as possible. And now for the first iteration, we're going to train our data in all these points. These are the ones that are smaller circles. And we are leaving the first ones out, this first block out. This is used to compute the validation error. So this is the training error here. This is the Breyer score I'm using in this case, and the validation error. And now we're going to repeat this, but we're going to leave those one out. So the second block is left out, and we are training with a slightly different set of points. And now we compute again the training error and the validation error, and we keep doing that until we cover all the 5 blocks of points we used there. And now we have this set of different hypotheses. Note that the curve is not always the same because we are using a different set of points each time. And we have also different validation error measures there. But if we average everything out, instead of having the validation error as an estimate of the true error of one hypothesis, we have an average sampled over different data sets that gives us an estimate of the true error of that model when it's trained with data somewhat like this one that we have. So we have a better estimate of the true error of the model. So after we do this, we can average those validation errors. There is one special case when we use as many folds as data points. So you can imagine this, but leaving one point out at each time. In that case, it's called leave one out cross-validation. It's generally not used unless you have a very small data set. So if you have hundreds of points, you're not going to do this hundreds of times, just leaving one example out each time. But if you have, say, 10 points or 15 points, maybe it's better to use leave one out than to use fewer points for training. One problem that we may have, both in cross-validation and testing, is when we decide to leave some points outside, if we have small data sets or if our classes are very unbalanced, we may have some problems, for example, with having one test set that contains only examples from one class. That may be a very bad thing. So another issue that may arise, especially with small data sets, is the need to try to balance these partitions. So we can use stratified sampling, which basically, if you want to split your data set, let's say 2/3 for one thing, 1/3 for another, you try to do it at random, but in order that both the test set and the training set have the same fraction of representatives for each class. So basically, stratified sampling is random sampling all the same, but with the constraint that we keep the same proportion of the different classes in all the data sets. So let's see an example how we can use this. Let's imagine we have this data set here. We want to find the best way to classify this point. And we're going to start by loading the data and standardizing. So this is, we're going to use this load txt for loading the text file into a NumPy array, so a matrix of the points. We can use this method, shuffle, from scikit-learn utils. You have this utilitarian method. Basically, it gives you a randomized view on the matrix. If you use it on a matrix, it amounts to shuffling the rows of the matrix. So remember that it's not shuffling in place. It gives you a view on that matrix, so you have to store the result in another variable. But this basically loads the data and shuffles everything up. This is useful because sometimes the data that you have are correlated because of the order. Say, if you are taking samples across many different days, you have samples that are close together, probably were taken with similar weather or something like that, and this may affect what you're trying to do. So it's often a good idea to randomize the order of your data before working with it, because that may be important. And now we're going to copy the features on one array. The classes. So the classes are the last column of the matrix, and the features are all columns. The first column on the matrix, and the features are all columns starting from the second one. And then we're going to compute the mean and the standard deviation for the features. These two standardize. We're going to subtract the mean and divide by the standard deviation. Note that depending on the number of features, these will be vectors that can have any type. But you can do this easily because of the way NumPy broadcasts these operations over the matrix. This is what you saw last week in the tutorial. You did some exercises with this. So if you are in doubt how this works, you can look at the broadcasting rules, or you can actually experiment with small matrices to see. So every time you're not sure how to use this, instead of starting to implement loops or things like that and get lots of messy code, just take a look with a few simple examples until you understand, and then use this, because once you get used to it, it makes this kind of work a lot simpler to implement. So now we want to test our classifier in different dimensions. Remember that trick of using the linear discriminant, but a linear discriminant in higher dimensions after a nonlinear transformation. When we backtrack that transformation, we can actually get curves to separate our data points. So this is what we're going to do here. We're going to expand our matrix with two features. We're going to expand it to 16 features by adding terms like the square of a feature, products of the two features, and so on. So we can do that with one function. We receive the matrix with two features. We create a new expanded matrix with 14 more columns than the first one. Remember that shape is an attribute of the NumPy arrays that tells us how large they are in each dimension. So shape 0 is the number of lines, shape 1 is the number of columns for the matrix. And now we're going to copy the original values to the first two columns of our expanded matrix. This is just the original data. And now we're going to start adding expansions. So the third column is the product of the two features. The fourth column is the square of the first feature, and so on. As long as all these transformations are nonlinear, we are expanding our data into a surface in n-dimensional space, but a surface that is curved because of these nonlinear transformations. So once we cut that with a straight plane and we project it back, we get all these curves in our classification. So we're going to create this large matrix with 16 features, and we're going to use this train test split function that randomly splits into training and test. We're going to split both the data matrix and the categories, the classes. We're going to say how much we want for the test, which this is 1/3, and we're going to stratify our sampling by giving the class labels there. This means that the training set and the test set will have the same proportion of points in each class, and we are not risking in one of these sets having a very different value than the other. You don't need to memorize these these functions because you have the access to the documentation. You just Google the functions and you see what options you can use. So the idea here for the code I'm showing you is not for you to commit it to memory so you can do it by heart, but just remember that you can do these things, and then when you're going to do them, just Google and look at the examples in the documentation. So now we're going to use k-fold cross-validation, and we're going to use this class to generate the index for the fold. So basically what we say is we tell this the class builder constructor how many points we have and how many folds we want. And this returns an iterator that we can use in a loop that each time each iteration of the loop will return a tuple with two lists. One of the lists will be for the training set and the other list will be for the validation set. So if we loop this 4 times, the first time we have in the validation set the first 3 points and the other points for the training set. These are indexes that we can then use to index, say, the rows of our matrix or something like that. In the second iteration, the validation set shifted to the fourth, fifth, and sixth points, and the others are in the training set, and so forth. We can also use this stratified k-fold if we want to do k-fold cross-validation with stratified sampling. To do that, we need the class label. So this array here is a sample of the class labels. And we're going to call the stratified k-fold, giving it the class labels and the number of folds that we want. And this one will do the same thing, return an iterator that returns those tuples, the training set and the validation set. But now, since we have 3 1s at the end, it will no longer give us 9, 10, and 11 here, because if it gave 9, 10, and 11, they would all be on the same class. So it actually switched 8 with 9 so that it balances the different folds. During the iteration, you can use this distributive property of the unpacking that Python has, that when you are assigning one array, you can assign it to a multiple set of variables as long as the number of variables corresponds to the number of elements in the array. So since for each iteration, this iterator returns a tuple with these 2 lists, you can do the for loop with the 2 variables there, and you unpack that tuple into the 2 variables in each iteration of the loop. So you don't need to do that outside the line for the loop. So basically this is how you can easily use cross-validation, or use these classes to get the indexes for cross-validation and then apply this to your problem. So let's do this with logistic regression. We're going to compute the training and validation error for each fold using this function. We receive the number of features that we want to use. Remember that our X matrix with the features is very large, but we may want to use only the first 2 columns or 3 columns and so on. We're going to receive the features and the class labels, the indexes for the training set and the indexes for the validation set, and this is the regularization parameter I'm going to talk about a bit later on. So we're going to create a logistic regression object with that regularization parameter, and this tolerance value is just for the numerical minimization of the error, to tell it when to stop. So when the difference is smaller than that tolerance, it stops the minimization. Then we're going to fit our training data, and our training data comes from the features matrix, using only those rows we specified for the training set, and only the first number of columns corresponding to this feature variable. So if we want to do it with only the original data, we tell it to do it with the first 2 columns. If we want to include the expansion with the product of the 2 first features, we say 3 columns, and so forth. And then we're going to use also the corresponding class labels. This is the ipsilon vector using the same indexes. So this is for adjusting the parameters. We are going to adjust the parameters of the logistic regression. After we do this, we predict the probability of those points that are outside the training set. So the ones we predict the probability for all the points, and then we compute the error for those points outside the validation set and inside the validation set. Now, predict probability gives you values for all the points, and then it gives you a matrix with different values. But you can look at the documentation to see exactly what it returns. In this case, the actual probabilities are in the second column of the matrix that we get. So these are the predicted probabilities. We subtract the class labels, which are 0 and 1, and square that to get the Breyer score. So basically, we are computing the quadratic error between the predicted probability and the class for each point, and then we are dividing that, we are averaging that error for the training set and for the validation set. So we return the two errors, the Breyer score for the training point and the Breyer score for the validation point. Now we're going to do this for different models. We're going to do this with cross-validations, So we're going to loop through from 2 features to all 16 features, and we're going to use this stratified k-folds so that we can split everything and keep the same balance of both classes, and we're going to use 10-folds. So for each model that we have, from 2 to 16 features, we're going to do this 10 times. So we're going to do cross-validation, so we have to train 10 times and use those 10 validation errors. We're going to obtain from our objects for the k-fold cross-validation the training and validation indexes. We're going to compute the training and validation error using that function, and then we're going to add everything, and in the end we print the average, the result, for example. So this is an example of what would happen if we use 2 features. These are the 10 different classifiers we trained with these 10 fold cross-validation. So each of these lines corresponds to leaving out 1/10 of the points and training with all the others. And the other line, we leave out another part of the training set and train with the rest, and so forth. And then in the end, we have on average a training error of 0.09 and a validation of error of 0.1. And now we can do this with more features, for example, with 6 features. So basically, we are still doing linear classification, but we are using a hyperplane in 6 dimensions after a nonlinear transformation. And then when we come back, this results in those curved lines between the points. So now we have a lower training error and also a lower validation error, but eventually when we go up to many features, our validation error starts increasing again. Notice that in this case the training error is 0, because for each fold it was always possible to find a solution for the logistic regression that perfectly classified all the training set. However, it then made worse mistakes outside, and so the validation error becomes higher. So we can plot this, and it looks like this, the plot. This is the training error as a function of the number of features. Here we are underfitting. Our model is too stiff to be able to classify those points. Then we can classify it correctly, and from this point on, our model is sufficiently flexible to, no matter which points we give it, it can classify them correctly. But in the validation error, we start decreasing, but then we start increasing again. So we can see that around here, degree 9 or 9 features is the best expansion for us to use. This would be the best of the models we tried. So now, after we do cross-validation, we retrain the best model with the complete training set. Remember that each of these curves was computed with only 90% of the training set, because we left 10% out for the cross-validation. So now, after we decide that our best model is the one with 9 features, we train that model with all the training sets. And since we would like to have an estimate of how this model will perform outside the training set, we retained initially that test set that we never used for anything, and so now we evaluate the error, the test error of our model on that test set. And this gives us an unbiased estimate of the true error of this final hypothesis. So, to recap this part, we start by pre-processing our data, whatever we need, but usually it involves shuffling the data to remove any correlations in the ordering we have, normalizing, standardizing the data depending on what we want to do. Remember, normalizing is that transformation that puts everything between 0 and 1. Standardizing gives everything a 0 average and a 1 of standard deviation. So you subtract the mean and divide by the standard deviation. Then we reserve a test set. We may want to do this with stratified sampling to avoid unbalancing the classes. And we partition the training set, which is what is left over, into n folds for cross-validation. Now we use cross-validation to select the best model if we have several models. In the end, we train the best model with all the training sets, and this is our final hypothesis. Now here there is a conceptual difference that is good to remember. When you're using cross-validation, you are averaging the validation error of different hypotheses. So you do not have an average. That average is not the error estimate of one particular hypothesis, but something you're using to evaluate the model in general. You're saying that this model in general will produce hypotheses that on average perform this way. But once you finish all the job, you have your final classifier, which is a single hypothesis. And it's useful to have an estimate of the error of that specific hypothesis that you already trained and that you're not going to train anymore. So that is what you use the test set for. At the end, you use the test set to get an estimate of the true error of that final hypothesis. So let's see another way of solving the overfitting problem, which is regularization. In model selection, we are trying to select the best model to balance the problems of underfitting and overfitting and to get the best performance. With regularization, what we do is we change our cost function. For example, we change something in the way we're training our model in order to prevent it from overfitting our data. So we're going to see how this happens in logistic regression. We can use this regularization in logistic regression with the L2 norm, which is basically adding to the cost function a penalty that is proportional to the sum of the squares of the coefficients. So we're trying to put the coefficient values as small as possible. In scikit-learn, instead of that lambda value there, we're going to use a C value, and the weight of the regularization factor is 1 over C. So the higher the C, the smaller the weight of the regularization. We'll see why it's done this way when we look at support vector machines later on, because this is a way to put all these classifiers using regularization factor that works in the same way. But basically, remember that C, 1 over C is equal to lambda. So in this case, we're going to use C. Higher the C, the smaller the weight of regularization. Now, with ridge regression, which is the regularized form of linear regression that we saw initially, this is intuitive. We have some function g that we are using for the regression, for example, a quadratic curve, and we are adding this term to our error function, which makes the coefficients as small as possible. So instead of our curve jumping up and down too much, it tends to become smoother because we don't allow the coefficients to be too large. So it's easy to see how reducing the size of the coefficients works for regularizing the regression, linear regression, because the smaller the coefficients, the smoother and stiffer the line will be. So here we are weighting both the quadratic error and the size of the coefficients. Depending on this lambda, we can allow the curve to adjust more to the point or not as much. In logistic regression, this is not as immediately obvious why reducing the values of the coefficients should make that difference. Because remember that these coefficients are those that define Yes?
The line becomes stiffer in the regression because basically the penalty is lower because of the one under C.
No, if you are penalizing these theta values here. So if you write a curve, say a polynomial with smaller coefficients, the curve will tend to be smoother. If you allow the coefficients to be too large, it can. So since you're adding a penalty that is a function of the size of the coefficient, it will tend to smoothen the curve. The thing is that with logistic regression, it's not obvious what effect that will be, because the coefficients are those that define the plane, and keeping these coefficients small, we don't see immediately what effect this is having on the classifier. But I'm going to show you why doing this, so adding this penalty to the cost function can help us here. So our coefficients define this plane that divides the data set. So in this example would be a three-dimensional data set. We have this plane here splitting the two. Reducing these coefficients would not necessarily change the place of the plane, as long as you keep the right proportions and you're not forcing the plane to change anything. You're basically just changing the magnitude of this vector. You can have a large vector here or a small vector, but they still define the same plane where that operation is zero. But it does make a difference on the logistic function, because if you have arbitrarily high values here, the value of the logistic function can change very quickly from 0 to 1, because it has very large values, or very small values after this exponent over here, and it becomes 0, or very large, very large here, and very small over here, and the shift is very abrupt if you have very high coefficient values. But if you force the coefficient values to be low, you force this slope to be a bit more, to have less inclination and go up a bit smoother. Although the plane divided is still the same, so this plane can be the same regardless of the size of the vector, the slope of the logistic function at that plane can change depending on the size of the vector. And the effect this has is that if you allow the coefficients to be very large, you can have it to be 0 here and then abruptly change to 1 and be 1 over here. So if you're minimizing the logistic error, you can put your plane here and still classify everything correctly. However, this is a bit suspicious, because this isolated point here is probably that kind of noise we don't want to fit, and this may be a case of overfitting because we are dividing the two classes just practically based on that point. If we use regularization, if we penalize the size of the coefficients, we force the slope to be not to be as high, and we force the plane to be placed here in order to minimize the error. Because now, if we were to place the midpoint of our logistic function here, we would have it very low on that side and get a very high penalty because of those points. So the plane gets shifted here, and this now is a much smoother slope, increasing up to 1 over on this side. So this is the effect of regularization on logistic regression. The size of the vector does not by itself force the plane to be different, but when we don't allow the slope to be as steep, we may have to change the place, the optimum place for the dividing line, because it's computing the error over all the points. So we're going to choose here the 15 features example that we had from before. So this has a lot of overfitting, but you see you have an average training error of 0, but we have a high cross-validation error. But now we can reduce the overfitting using regularization. So what we're going to do is to change these C values. So the weight of the regularization factor is 1 over C. If we use small c, we are imposing a large regularization penalty, and we are forcing the slope to be very, very low. And if we have a large c, we are reducing the weight of the regularization penalty, and the coefficients can be larger. And we can plot this. This is a training error in blue and the cross-validation error, so it goes down here and then it rises a bit again. This is a logarithmic scale. This is the logarithm of C. And we have this optimum C, which is 10 raised to the 5. So this is 1 over C is the weight we're going to give to the regularization factor. Typically, it's a very small weight because we don't want to force too much the classifier, but it's enough to result in a better curve, and actually this one has a test error of 0, although this may have been by chance. So to sum up, we saw how to score and evaluate classifiers. We have different scoring schemes. We saw cross-validation for model selection. This is better than what we have seen so far, but it's good to start slow and to get an idea of what we're trying to do. Basically, with cross-validation, you are averaging the validation error over different hypotheses and gives you a better estimate of the true error of the model. So how the model would perform in this kind of data. After we select either the best model or the regularization parameter or both, because we can use cross-validation to select all of these things, it's useful after training with the whole training set. We get the final hypothesis, and it's useful then to get an error estimate for that particular hypothesis. Because if that's the classifier we're going to use, we should have an error estimate of that classifier. So for this, it's good to retain a test set outside everything that we use. Sometimes this is not possible because we have small data sets, and maybe it's not a good idea to lose more data for the test set. But if you can do it, it's useful to have this final evaluation. We also saw stratified sampling. Stratified sampling is a very simple idea. You are splitting at random, but trying to keep the same balance between the different classes. And you can use stratified sampling for separating the test set and also for the different folds in cross-validation. So you can read more about this part in the section 2.7, and if you have questions.